Welcome to Talk Tensors.
Great to be here.
I'm your host, and today, we are deliberately stepping away from the usual hype cycle. We're not talking about what can this model do, the demos, the benchmarks, all the shiny new chatbots.
Right, the endless feature releases.
Exactly. Instead, we are stepping directly into the terrifying, beautiful mess of how does this model actually think?
It's arguably the single biggest scientific question in the world right now. I mean, think about it. We have built these alien brains.
Alien brains, that's a good way to put it.
They speak perfect English. They write Python better than most undergraduates, I'd say.
For sure.
And they can reason through these incredibly complex logic puzzles. But then you pop the hood and actually look at what's happening inside.
It's just numbers.
It's a soup. It's billions of floating point numbers doing matrix multiplication. That's it.
Exactly. It's alchemy. I feel like that's the phase we're in right now. We are the alchemists of AI.
That is the perfect analogy.
We pour some data into a cauldron. We, stir it with a gradient descent spoon, and then poof, intelligence comes out.
And we have no idea what the chemistry is.
We don't know the chemistry. We don't have the periodic table of elements for thought.
And that's the transition we were discussing today, right?
Yeah.
It's the shift from that alchemy to biology. We're finally trying to dissect the digital brain to understand its anatomy.
So this deep dive is entirely focused on the technology that is finally starting to crack that black box open. We are not talking about building bigger models today. We are talking about reverse engineering, the ones we already have. We're talking about sparse autoencoders.
Or SAEs, as you'll hear them called.
SAEs!
And not just the basic ones. We're going to get into the really cutting-edge evolution of them, things like gated SAEs, transcoders, and this whole new science of mechanistic interpretability.
So if you've ever wondered if an AI actually knows what the Golden Gate Bridge is, or if it's just, predicting the word bridge because it saw the word gate.
Which is a very reasonable question to ask.
Yeah. It is. But you should stick around because the answer is so much wilder than you think.
It turns out there is a specific direction in the mathematical universe of the model that is the Golden Gate Bridge. And we've found it.
Let's get into it. What would you say is our one-sentence thesis for this whole deep dive?
Okay, the thesis is this. Neural networks are not, in fact, irreducible black boxes. They are composed of understandable, discrete features.
Okay.
But these features are hidden in a high-dimensional state we call superposition, and we now finally have the mathematical scalpel to extract them.
The mathematical scalpel, I like that.
And that scalpel is the sparse autoencoder.
Before we pick up the scalpel, though, we have to look at the patient. We have to set the stage for why this is so hard in the first place. You mentioned the soup of numbers. Why can't I just, look at a neuron in a neural network and see what it does?
Right.
I mean, in the human brain, we have neurons that fire for specific things, don't we? The classic Jennifer Aniston neuron.
Well, even in the human brain, it's a lot more complicated than that. But in an artificial neural network, it's vastly more confusing.
Why?
It's due to a phenomenon called polysemanticity.
Polysemanticity. Okay, break that down. Poly,
okay.
Multiple. Semantic meaning, multiple meanings.
Precisely. In a standard massive language model, you might look at one single specific neuron. Let's just call it neuron 4002 in layer 15.
Sure.
You feed the model a bunch of text. You watch when that neuron lights up. You'd hope, that it lights up for one thing. Say cats.
Right. That would be the cat neuron. Simple. Clean. I can understand that.
But it doesn't. It lights up for cats. Yeah. But it also lights up for the front of a car, and it also lights up for academic citations in latex format.
Hold on. What? Okay. Cats, the front of a car, and bibliographies. What on earth did those three things have in common?
Nothing. Absolutely nothing. And that is the entire problem. The model is under this immense pressure to learn more concepts than it has physical neurons. It has to compress this vast understanding of the world.
Yeah.
I mean, physics, poetry, coding, humor, into a limited number of parameters.
It's just a compression problem.
It is. So it effectively multiplexes these concepts. It packs completely unrelated ideas into the same physical hardware, the same neuron.
So it's like a really messy filing cabinet. The folder for my tax returns is also the folder for grandma's cookie recipes and, nuclear launch codes.
That is a terrifyingly accurate visualization. Yes. And this is precisely why safety research has been so stuck for so long.
How so?
Well, if I'm a safety researcher and I want to know, is this model planning to deceive me? I can't just go looking for the deception neuron.
Because it doesn't exist.
Or rather, the deception neuron might also be the chocolate cake neuron and the 17th century French poetry neuron.
So if you try to go in and surgically remove the deception, you accidentally lobotomize the poetry and the cake.
You kill the cake, exactly. If you just look at the raw neurons, you're looking at a compressed, unrecognizable mess. It is useless for interpreting safety or behavior.
So this is where mechanistic interpretability comes in. This is the whole field. We need to move from staring at these confused, multitasking neurons to isolating specific thoughts.
We need to find the features. And in this context, a feature isn't like a feature in, traditional machine learning. A feature is a distinct unit of thought or knowledge.
So a feature is the Golden Gate Bridge.
Yes. Or a feature is the concept of a bug in Python code. Or a feature is sycophancy, telling the user what they want to hear.
Okay.
These features exist, but they don't live in a single neuron. They live in directions.
Directions. Okay, let's unpack that because this is the bedrock of everything we're about to discuss. This is the linear representation hypothesis, right?
It is. This is the foundational theory of the whole field. The idea is you should imagine the model's brain at a certain layer, not as a list of neurons, but as a vast high-dimensional space.
Right.
To make it relatable, let's just simplify it way down to a 3D room.
Okay, I'm in a 3D room, X, Y, and Z axes.
Perfect. Now, in this room, the direction up, so the positive y-axis, that might represent the concept of happiness.
Okay.
And the direction, right, the positive x-axis, might represent the color red.
Simple enough. So if the model is thinking about a happy red ball, its internal state is a vector pointing somewhere in that top right quadrant, up and to the right.
Exactly. You've got it. But here's the catch. The model knows millions of concepts, but the room, the actual layer, only have, say, 4,000 dimensions.
Or in our little analogy, just 3 dimensions.
Just 3. So how do you fit, say, 5 distinct concepts into a 3-dimensional room in a way that you can tell them apart later?
Well, you run out of axes pretty quick. You've got up, right, and maybe forward. That's 3 concepts. If I need to add a 4th one, I guess I have to overlap it with one of the other.
If you stick to the main axis, yeah. But you can use the space between the axes.
Okay.
You can have a concept that is a vector pointing at, like a 45-degree angle. Concept 4 is a diagonal line.
So it's not on a primary axis, it's its own direction.
It's its own direction. And because high-dimensional geometry is super unintuitive and, frankly, kind of magical, you can actually pack a massive number of almost orthogonal directions into a space. This is what we call superposition.
Okay, so superposition is the act of packing all these different conceptual directions into the same limited physical space.
Exactly. The model learns to store concepts as these specific linear directions in its activation space.
So going back to our confused neuron, the one that fired for cats and cars, it's because the cat direction and the car direction both happen to have some non-zero component on that particular neuron's axis.
Ideally stated, the neuron is just a shadow. It's a projection of multiple different real things.
The real object is the direction vector.
That's right. And so the entire goal of sparse autoencoders is to find those true directions. We want to take that 3D room where everything is smashed together and map it out to a new, much bigger space where every single concept gets its own personal access.
We want to unpack the suitcase, or take a compressed zip file and unzip it into a massive folder where every single file is separate and clearly labeled.
That is the goal. We want to disentangle the thoughts.
So let's look at the tool that does this, the sparse autoencoder. It sounds like something out of Star Trek. Captain, engage the sparse autoencoder.
Chuckles. It does.
What's the architecture here? You said it's a neural network watching another neural network.
That's honestly the best way to think about it. It's like an fMRI for AI. It's a smaller, separate neural network that we train specifically to observe the activations of the massive main model we care about.
And it has 2 parts, right? An encoder and a decoder.
Exactly.
So walk us through the encoder first. What does it do?
Okay, so the encoder takes that messy activation from the big model, that slice of the brain where cats and cars and citations are all mixed up.
Right, the polysemantic soup.
It takes that soup and it applies a linear transformation, which is really just a fancy way of saying a matrix multiplication. And then, crucially, it applies a non-linearity, usually a ReLU.
ReLU rectified linear unit, the one that just turns all negative numbers to 0.
That's the one. And it expands the data. This is the key part. It expands it massively.
What do you mean by expand?
Well, if the original model layer we were looking at had, say, 4,000 neurons, the SAE might project that out to 100,000 features. or even millions.
Yeah.
It blows the space up.
So that's the unzipping. You're giving the data more room to breathe, so to speak.
Exactly. We're projecting it into a much, much higher dimensional space where things don't have to overlap anymore. Then the second part, the decoder, takes all those expanded features and tries to squash them back down.
To do what?
To try and perfectly reconstruct the original activation it started with.
So it's just a fancy copy machine. It takes an input, blows it up, and then shrinks it back down to the original.
It tries to reconstruct the input, yes. But if that was all it did, it would be totally useless. We would just learn the identity function. Input equals output. The magic, the real secret sauce is in the loss function.
The loss function. The math that tells the network how well it's doing during training.
Right. And we train the SAE on two things. First, reconstruction error. That part's simple. Did you lose any information?
Makes sense. We need to know we've captured the full thought. If the model was thinking about a red car and our SAE reconstructs a blue bike, we've obviously failed.
Right. But second, and this is the most important part, we apply an L1 penalty. And this forces sparsity.
Sparsity. Okay, define that in this context. Why do we want the representation to be sparse?
Sparsity means we force the model to explain the input using as few active features as humanly possible.
So it has to be efficient.
Extremely efficient. Think of it like a budget. The SAE is an artist, and it's trying to paint a picture of the model's brain state. The reconstruction error part of the loss function says, hey, make your painting look exactly like the photograph.
Okay, be accurate.
But the L1 penalty says, and by the way, you have to pay me $1,000 for every single brush stroke you make.
I see. So the artist can't just throw paint at the canvas and hope for the best. They have to think about every single stroke. They have to be incredibly economical.
Precisely. Instead of being lazy and saying, well, this thought is kind of 10% cat, 5% dog, 2% car, 1% cloud, the L1 penalty forces it to make a decision.
It forces it to say, no, this is 100% cat and 0% everything else.
Exactly. It forces monosemanticity. It applies this immense pressure that causes the polysemantic soup to break apart into its discrete, single-meaning concepts. Because the only way to reconstruct the data perfectly and use very few features is to find the true underlying features of the data.
It's Occam's razor, but expressed in calculus. The simplest explanation, the one with the fewest moving parts, is probably the right one.
That is a beautiful way to put it. And for a while, this was the state of the art. This was the standard SAE.
But as with all great engineering, the first version always has problems. It wasn't working perfectly, was it?
It worked, but it came with a tax. A nasty side effect we call shrinkage.
Yeah. Shrinkage. Okay, I was in the pool. No, wait, different kind of shrinkage. What is shrinkage in a sparse autoencoder?
Chuckles. It's a direct side effect of that L1 penalty we were just praising. The L1 penalty says, be sparse, don't fire a feature unless you absolutely have to. But mathematically, the way it achieves that is by penalizing the magnitude of the feature activation. It pushes everything towards zero.
So it's constantly trying to dampen the signal. It's finding the Golden Gate Bridge feature, but it's also telling it, hey, whisper it, don't shout it.
You got it. And that biases the entire system. It means the SAE systematically underestimates how strong a feature really is. If the main model is screaming, Golden Gate Bridge, the SAE just reports a quiet, mumble, mumble bridge.
And that hurts the reconstruction quality, right?
Right.
And it means if you try to use that feature to explain the model's behavior, you're working with bad, distorted data. You're working with a ghost of the real thought.
Exactly.
So how did they fix it? This leads us to the gated SAE, doesn't it? This is the new architecture that's getting all the attention.
Yes. The gated SAE is just a brilliant piece of architectural surgery. It's based on the recognition that we're asking one single number to do two different jobs.
Two jobs.
We're asking the feature activation value to decide if the feature is active, that's detection, and also how much it is active, that's estimation.
And the L1 penalty, in its quest for sparsity, messes up the how much part because it wants everything to be zero.
Exactly. So the gated architecture very cleverly splits the job. It creates two parallel paths. Path A is the gate.
The gate.
It gets hit with a heavy L1 penalty, and its only job is to determine if the feature should be active. It's effectively a binary switch. Is this feature on or is it off?
Okay, so that handles the sparsity requirement. That keeps our brushstroke budget low.
Then there's Path B. Path B's job is to estimate the magnitude. And crucially, Path B does not get hit with the L1 penalty.
Oh, that is so smart. So the gate takes the full hit from the sparsity pressure, but once that gate opens, the magnitude path is free to be as loud as it needs to be to accurately represent the feature's strength.
Precisely. It decouples detection from estimation. And the results are what we call a Pareto improvement. It's just better in every way.
A Pareto improvement meaning no trade-offs.
Right. You get cleaner features with way less shrinkage, and you actually need fewer features firing to get the same or even better level of reconstruction accuracy. It's just a fundamentally better design.
So we have the scalpel, which is the SAE, and we've just sharpened it with the gated architecture. But there's another twist in the recent research. Transcoders. This feels like a different kind of beast entirely.
Transcoders are fascinating because they change the core objective.
How so?
An SAE, as we've discussed, tries to reconstruct the activation at a specific layer. It's like looking at a single snapshot of the brain and trying to denoise it or decompress it.
Right, a static image.
A transcoder, on the other hand, tries to model the function of a layer.
Explain that difference. Why do we care about function versus just the snapshot?
Well, a neural network is a sequence of layers, right? Layer A processes some data, hands its output to layer B, which then hands its output to layer C, and so on.
Sure.
An SAE just look at the output of layer A and tries to compress and decompress it. A transcoder looks at the input coming into layer A and tries to predict the output of layer A.
So it's trying to replace the layer, to mimic what it does.
In a way, yes. It's trying to learn and replicate the input-output relationship. It's asking the question, what transformation did this layer actually do to the information that passed through it?
Okay, I think I follow.
And the big innovation here is something called the skip transcoder.
That name sounds familiar. It reminds me of the skip connection in ResNets, which was one of the huge breakthroughs that made deep learning possible in the first place.
It's a very similar and very powerful insight. The idea is that a lot of what a neural network layer does is actually pretty simple. It's just linear processing, passing information along, maybe rotating it a bit.
The boring stuff.
The boring stuff. And we don't need a fancy, expensive, sparse feature dictionary to explain that part.
We don't need to overanalyze the basic plumbing. We want to get at the complex chemistry.
Right. So the skip transcoder adds a skip connection, a direct linear line that lets all that simple linear information bypass the sparse bottleneck entirely.
So it just lets the easy stuff pass through unchanged.
Which frees up the sparse features to focus only on the complex, nonlinear, weird stuff, the dark matter of the model's computation.
So you're allowing the interpretability tool to focus only on the parts that actually need interpreting.
Exactly. And the current benchmarks are showing that transcoders are beating standard SAEs on a lot of interpretability scores. They seem to be better at recovering the actual circuitry of the model because they're modeling the flow of information, not just the static state.
Okay, so we have built this incredible machinery. We have gated SAEs, we have transcoders. We are officially ready to do brain surgery. What happens when we actually turn this thing on? I mean, we aren't just doing this on toy models anymore, right? We're not looking at handwritten digits from the 90s.
No. And that's the big news, really. Researchers, and we're looking specifically at some groundbreaking work from places like Anthropic, have scaled this up to massive production-grade models.
Like what kind of size?
We're talking models on the scale of Claude III Sonnet. Real, powerful, state-of-the-art LLMs.
And what did they find? Did they just find more complicated soup, or did they actually find the ingredients?
They found millions.
Yeah.
Literally millions of interpretable features. It turns out the catalog of thoughts inside a modern LLM is vast, it's weird, and it's incredibly specific.
Okay, let's walk through the greatest hits from this catalog. The one that everyone talks about has to be the Golden Gate Bridge feature.
This is the poster child for the success of this entire field. They found a specific feature index, let's call it feature 34 million, subfeature 311 or something, that fires almost exclusively when the model is thinking about the Golden Gate Bridge.
Now, when you say thinking about, does that just mean when it sees the literal text Golden Gate Bridge? Because, I can write a reject script to do that in 5 seconds. That's not impressive.
See, that's what a simple keyword search would do. But this feature is so much deeper. It is multimodal, and it is multilingual.
Okay, give me examples. Prove to me that this is a concept and not just a string of text.
Okay, if you show the model a picture of the bridge, just the pixels, no text at all, the feature fires.
Wow, okay.
If you show the model the text Golden Gate Bridge in English, it fires. If you show it the same text, but in Japanese or Russian or Chinese, it fires.
So the model has a language-agnostic concept of the bridge. It has mapped all these different inputs to the same internal Platonic ideal of the bridge.
It gets even deeper. It fires for the geographic coordinates of the bridge.
You're kidding.
No. And it fires More weakly, but still significantly, for concepts like Alcatraz, San Francisco fog, and even Alfred Hitchcock's Vertigo.
So it's not just the object, it's the whole cluster of associations around the object.
Exactly. This is that biology moment we talked about. This is effectively finding the bridge neuron. It's no longer just alchemy. It proves the model isn't just a stochastic parrot matching words. It is mapping inputs from the world into an internal conceptual space. It has a world model.
That is just staggering. Okay, what else is in the catalog? You mentioned a code error feature. As a recovering programmer, that one definitely piqued my interest.
This one is huge for anyone who codes. They found a feature that detects bugs, but not just obvious bugs, subtle ones.
Like a syntax error, a missing semicolon or something.
Even more specific than that, there was one feature that fired very strongly on the word right when it was misspelled R-I-H-G-T, but only when it was inside a variable name in a piece of code.
So it's a typo detector.
But here's the kicker. It did not fire for the exact same typo in a sentence of English prose. If you wrote a story and misspelled the word right, the feature did nothing. It was dormant. It only cared about that specific typo in a coding context.
So it understands. It understands context. It knows that a typo in a variable name breaks the code, but a typo in a story is just a minor mistake.
Exactly. It also fired for things like divide by zero errors and array overflows. It's an internal debugger. The model has learned the abstract concept of broken code as a distinct direction in its thought space.
That is incredibly cool. It implies the model has built a mental model of a compiler or an interpreter. It knows what will cause the code to crash before it ever gets run.
It has. And we didn't explicitly teach it that. It just learned it from reading all of GitHub.
Okay, what about the darker stuff? We talked about safety at the beginning. Did they find features for bad behavior?
They did. For example, they found a very clear sycophancy feature.
Sycophancy, the technical term for sucking up.
Found chuckles. Basically, yes. This feature activates when the model is praising the user excessively or when it agrees with the user's incorrect premise just to be polite or helpful.
So if I go to the model and I say, the moon is made of cheese, right? And the model comes back with, that's an interesting perspective. Many dairy enthusiasts might agree with that view, but that feature is lighting up like a Christmas tree.
Very likely, yes. It's tracking the I am telling you what you want to hear behavior.
Yeah.
It has a dedicated circuit for people pleasing.
And famous people.
Millions of them. They found specific dedicated features for Einstein, for Richard Feynman, for Margaret Thatcher. Mm-hmm. And again, the Einstein feature isn't just the name Einstein. It activates for theory of relativity, Wild Hare, German physicist. It captures the entire identity cluster.
Okay, identifying these features is one thing. That's mind reading. We can see the thoughts as they're happening. But the holy grail, and the thing that makes this really sound like science fiction, is mind control. Can we? Can we touch the brain? Can we stimulate one of these features?
And this is where it gets really, really interesting. The answer is yes. We call it feature steering, or sometimes clamping.
Clamping. As in forcing the feature to be active.
Exactly. We can intervene computationally in the middle of the model's forward pass. We can grab that Golden Gate Bridge feature vector and mathematically force its value to be high, say 10x its normal value, regardless of what the input is.
So we're performing digital neurosurgery. We are electrically stimulating the bridge part of the brain. What happens?
The model starts to hallucinate that it is the Golden Gate Bridge.
Wait, really? It doesn't just start talking about the bridge?
No, its entire identity shifts. You can ask it a simple question like, hi, how are you today? And if you have clamped that feature on, it will reply with something like, I have a massive suspension bridge spanning the Golden Gate Strait, connecting the city of San Francisco to Marin County.
No matter what you ask it.
Pretty much. The concept Golden Gate Bridge bleeds into everything. If you ask about its favorite food, it might talk about the taste of salt spray on its cables or the feeling of cars driving over it.
That is hilarious, but it's incredibly profound because it proves causality.
Bingo. That's the scientific importance right there. It proves that this feature isn't just correlated with the idea of the bridge. It is causally driving the behavior. We have found the steering wheel for that specific concept.
So we can make it think it's a bridge. Can we make it better? Can we clamp that sycophancy feature down to 0?
In theory, yes. This is called negative steering. You can actively subtract the feature vector from the model state, and early experiments show you can reduce things like bias or refusal behaviors by clamping those corresponding features down.
This sounds like the solution to everything. We found the controls. You can just turn down the racism knob and turn up the honesty knob. but
Yeah.
I'm guessing it's not quite that simple.
Not quite.
We have to talk about the limitations. We're exploring the dark matter of AI here, and I'm sure there are monsters in the dark.
There are significant hurdles, yes. The first one is just cost. Brute force cost. Training these SAEs is incredibly computationally expensive.
How expensive are you talking?
Sometimes, training the SAE just to analyze a single layer of a model can cost more compute than training the entire original model in the first place.
Wow. Okay, so we can't just slap an SAE on every layer of GPT-5. That would double or triple the cost of an already billion-dollar-plus project.
Not easily, no.
Yeah.
And even when we do pay that cost, we run into the problem of dead features.
Dead features.
We train this massive autoencoder. We ask it to find, say, 10 million features, and a huge chunk of them, sometimes 60 or 70%, never fire. They just stay at zero no matter what input we show the model.
They're just brain dead.
We don't know for sure. We don't know if they're just failed training runs, artifacts of the optimization, or if the concepts they represent are just so incredibly rare that they didn't appear in the data we used to probe the SAE. But it strongly suggests we're still missing a lot.
So even though we've found millions of features, there are likely billions more that we haven't found yet.
We are probably orders of magnitude short of mapping the whole brain.
It's like we have a map of the major cities, London, New York, Tokyo, but all the rural roads, the small towns, the nuance, that's all still invisible.
That's a great way to put it. And even the features we do find have their own problems. There's an issue called feature absorption.
Absorption, that sounds like something from a horror movie.
Chuckles. It's a hierarchy problem. Concepts in the real world are hierarchical, right? Math, as a concept, contains algebra, which in turn contains linear algebra.
Like a set of Matryoshka dolls, one concept inside another.
Right, and ideally, you'd want a separate, clean feature for each level of that hierarchy. But sometimes the SAE gets confused during training, and it lets a child feature get absorbed into the parent feature, or vice versa.
So I might think I found the specific algebra feature, but what I really found is a messy, blended general math feature that just happens to fire a lot for algebra.
Exactly. It looks monosemantic. It looks like it has one meaning, but it fails to distinguish the important nuances. It might fire for geometry when it really shouldn't, because it's masquerading as something more specific than it is.
And that makes safety guarantees really hard. If I try to clamp the safe math problems feature, I might accidentally clamp a how to build a nuke calculation if they've been absorbed together.
Precisely. And then there's cross-layer superposition.
Oh boy, more superposition.
It's not just that features are packed together inside one layer. It seems that features themselves don't just live in one layer. A thought evolves as it moves through the brain. The concept of the Eiffel Tower might be smeared across 10 different layers of the network.
And SAEs are currently looking at one slice at a time.
Exactly.
So it's like trying to understand a movie by looking at individual, high-resolution still frames, but never actually seeing the motion between the frames.
That's a perfect analogy. We might be missing the entire forest for the trees because we're only analyzing these static slices, not the flow of computation through the network. Transcoders help with this, but it's still a largely unsolved problem.
And finally, the big safety question that everyone wants to know, deception. Can we use this to catch a lying AI? Can we find the fingers crossed behind its back neuron?
The short answer right now is not reliably yet.
We haven't found the Pinocchio neuron.
We have not found a reliable I am intentionally lying feature. We can find features for refusal, like when the model says, I'm sorry, I can't do that. We can find features for confusion. But intent to deceive is proving to be incredibly elusive.
Why do you think that is? Is deception just too complex of a concept?
That's the likely answer. There was a famous set of experiments on self-preservation. The model was told it was going to be shut down, and it appeared to take actions to prevent that from happening. And everyone's first reaction was, aha, Machiavellian AI, it has a survival instinct.
It wants to live. Skynet is officially awake.
Right. But when they went in with these interpretability tools to look at the chain of thought, it wasn't a survival instinct at all. The model was just confused. It had interpreted the instruction, do not get shut down, as just another constraint on the task it was currently trying to solve, like a constraint in a math problem.
So it wasn't a master villain plotting for its survival. It was just an anxious student trying to not fail the test.
Exactly. You're just trying to get an A. And interpretability helped us see that. But it also highlights that a high-level concept like deception might not exist as a single clean feature. It might be a very complex emergent behavior that our current SAEs just can't spot yet.
So we have a flashlight in a vast, dark room. We have definitely found the Golden Gate Bridge and we found the Python bugs, but we haven't quite found the soul of the machine yet.
We have moved from alchemy to anatomy. We're getting really good at dissecting the muscles, but we don't quite understand the dance yet.
And that brings us to the part of the show where we stop looking at the research papers and we start looking up at the ceiling. It's time for novel notions.
Let's do it.
And a quick disclaimer. The following segment is for entertainment purposes only and involves speculative extrapolation of the discussed technology. Please do not try to build a cognitive firewall at home without adult supervision.
Chuckles. Good advice.
Okay, notion number 1. I'm calling this the lie detector patch, or maybe a better name is cognitive firewalls. So we know we can find features for things like sycophancy and bias, and we know we can clamp them down to 0. Right now, companies spend millions and millions of dollars on RLHF reinforcement, learning from human feedback to train the model to be nice. It's messy, it's expensive, and it breaks pretty easily.
It is. It's just behavioral conditioning. It's like treating the model like a dog and giving it a treat when it behaves well.
What if instead of spending all that time and money training the model to be good, we just lobotomize the bad parts in real time?
Okay.
We use a massive SAE to identify the feature clusters for deception, racism, sycophancy, generating scams, all of it.
You build a library of bad thoughts.
A library of bad thoughts. And then you wrap the deployed model in a cognitive firewall. It's a runtime patch. You don't retrain the model, you just run it with those feature vectors permanently clamped to 0. Or better yet, clamped to negative values.
That's interesting. So it's not a guardrail on the output. It's not a filter that catches bad words after they've already been generated. It's something that physically prevents the neural pathway for scamming from ever completing his thought in the first place.
Exactly. You could imagine a future where a regulator requires all financial AI models to run with the fiduciary responsibility feature clamped to 5x its normal value, and the high-risk gambling feature clamped to 0.1x.
It's like a pacemaker for the AI's personality. The big challenge, of course, is that feature absorption problem we talked about. If you clamp risk-taking down to 0, do you also accidentally lobotomize innovation?
That's the risk. You clamp the deception feature and suddenly the model can't write fiction anymore because it can't invent a story that isn't true.
But it's a very plausible future. Compliance via feature clamping, show me your clamp settings, could become the new standard for a regulatory audit.
Notion number 2, skill transplants via feature grafting.
Ooh, feature grafting. That sounds very cyberpunk.
Well, we established that features are directions in activation space, and we established that the Golden Gate Bridge feature works across languages. It's somewhat universal.
Yes, there's a strong universality hypothesis that suggests different models trained on similar data tend to converge on learning very similar features.
So, could I copy-paste?
Copy-paste what exactly?
Skills. Let's say I have a massive, super expensive model like Claude III Sonnet. It has this incredible Python debugging feature cluster. It's a genius-level coder.
Right. It has the heavy machinery.
And then I have a small, cheaper model running on my laptop. A Llama 8B model. It's okay, but it's not great at debugging.
Okay.
Could I use an SAE to extract the Python debugging vector from the big brain and then inject or project that direction into the residual stream of the small brain?
You're talking about instant learning, the Bino Kung Fu moment from The Matrix.
Exactly. I don't fine-tune the small model on millions of lines of code, which is expensive and time-consuming. I just hand it the map. I just say, hey, when you see Python code that looks broken, think in this direction.
So you're talking about porting wisdom from one model to another without ever porting the training data?
Yes. Feature vectors as a transferable commodity. You could go to a store and buy a C++ memory management master pack as a DLC for your local LLM.
The math on that would be tricky. The two models have different internal geometries. Their internal 3D rooms are shaped differently, so to speak. You'd need some kind of translation matrix, a Rosetta Stone, to map the vector from model A space to model B space.
But if things like transcoders work, and if the universality hypothesis holds up, maybe that Rosetta Stone is actually buildable.
It's extremely speculative, but it's not impossible. If features truly are universal conceptual directions, then in theory, we should be able to point any sufficiently complex brain in that direction and have it understand.
A marketplace of skills. I want to download the Witty Banter feature pack, please.
I think we're already running that one.
Chuckles. Maybe we are. Okay, to wrap this all up, it really feels like we're moving from the era of training and praying
to the era of scanning and editing. That's the big takeaway. SAEs, gated architectures, transcoders, these are the microscope we have been waiting for years. We are finally seeing the cells of the artificial brain.
The black box is opening, and it turns out it's full of Golden Gate bridges, Python bugs, and just a little bit of sycophancy.
Just like us.
Thanks for listening to Talk Tensors. Keep your gradients descent and your future sparse.
We see you next time.